Okay, thank you so much for joining us this month. Tonight's speaker is Brian Taylor of Cisco Systems. He's going to be covering data center optics and cabling. We did a run through on this yesterday. We're going to do another one today. It's a really great topic, and I hope you get something out of this. Brian, please take it away.
Thank you. So thank you for joining tonight. This is a presentation that has grown out of my own learning in the realm of data center optics. Had a lot of different customer engagements that have come up against some challenges when they were transitioning from like the 10 and 25 and 40 gig realm to the 100 and 400 gig realm. And, they started running into issues with their cabling plants and, just had to kind of look things up and learn things to kind of help them out. So I created this deck in order to kind of give some background information for those who are not super familiar with cabling. This may be a little basic for some of you, but bear with me because there is something hopefully to be learned by all. So a little bit about me. I've been in the IT industry for about 27 years. I joined Cisco in about 2009. Prior to that, I was at a number of different integrators and resellers, and then Compaq and then HP after the merger with Compaq. And then I left HP in 2009 and joined Cisco with the launch of the unified computing system. And I have been focused on data center technologies since I came to Cisco. Well, actually, since before Cisco. But in more recent years, I shifted from the compute and storage background to more of the network side of things, where I support the Nexus and the MDS product lines and all the different technologies that go along with that. I actually used to be a former SoCal resident, so I'm familiar with the area, and I happen to be living in Beaverton, Oregon right now, moved up a few years ago. That's actually a picture of me at the San Diego Wild Animal Park just prior to us moving up to Oregon. And if you guys have never been to the Wild Animal Park, it's definitely worth the trip to go there. All right. So a little bit about what we're going to be talking about today. And I will actually provide a copy of this deck to Jason to provide to any of the people who registered for this session, and we'll be able to get this deck out to you guys for reference purposes. So there are some appendices where I've got some tables regarding different transceivers that are available, breakout cables and such. But for the sections that we'll be covering in the talk today, we'll be talking about the physical cabling and connections. We'll talk about how the modular transceivers function, how we transmit data over fiber optic cables and copper cables using specific standards. We'll talk a little bit about the capability of doing Ethernet breakouts for 10 gig, 25 gig, 100 gig. And then we'll talk a little bit about the 10 gig Ethernet twisted pair small form factor pluggable transceiver that we have. And then we'll touch a little bit briefly on fiber channel connectivity and some of the different transceivers available for that. And then, like I said, the appendices are for reference for if you're looking up part numbers for, a particular transceiver and, how that works, what its capabilities are. So let's dive into physical cabling and connections. So one of the more common types of cabling that you're going to find pretty much all over your campus and your data center is going to be your traditional unshielded twisted pair or Cat5 as most commonly called. These are going to use your RJ45 connections. Not going to get too much into this. These are pretty familiar to most of the people on the call, I would assume. But I do want to bring this up when we're dealing with the data center. Typically, when we talk about copper in terms of cabling in the data center, we're not referring to unshielded twisted pair. We are generally referring to twin axial copper or twinax. So this is actually going to be a cable with two SFP pluggable transceivers soldered into either end, and these are going to basically just pass the electrical signal from device to device in the data center without actually converting it into an optical signal the way that other optical transceivers would do. When it comes to optics, there's basically two main types of cables that you're going to find in the data center. Single mode fiber was the most common one years ago when I started, and that was a pretty narrow fiber. You can see down at the bottom right there, there's a little diagram showing how wide the actual fiber is inside the cladding. And you can see on the far right, the single mode is a 9 micron wide wire, 9 micron wide optical fiber. And so it's narrow enough that you don't really have too many transmission angles that you can have for the light. And therefore you can maintain a cleaner signal and get the signal farther. So single mode fiber is generally used for long distance transmission as well as usually the higher speed communication tends to be certified on single mode fiber types of media before it goes into any of the other types. When you are dealing with shorter distances and not as high throughput, you're typically dealing with multimode fiber. It's generally much cheaper fiber. It's going to be a wider fiber optic cable, and basically it's typically going to be a 50 micron wide optical fiber. And what happens is when you shine the light into it, it will actually bounce off the walls, and it can do so at varying angles that are referred to as optical modalities. So depending on the number of optical modalities that are present in the cable, your signal can have some interference. And so we don't certify these cables for as far a distance as we do for single mode fiber. So whenever you see an OM designation on a cable, like the OM1 through OM5, it just means that the higher the optical modality number, the better or farther the signal is going to carry on it. So you'll see, for example, if I have a OM3 cable, it might be certified to carry a 100 gig signal for maybe 100 meters. But if I have an OM4 or an OM5 cable, it might be certified to carry it up to 150 meters. Another thing that you might see commonly in the data center is going to be what we call active optical cables. So active optical cables, there's no magic to them. They're usually going to be multimode fiber cables. And the only difference with these is they have the transceivers permanently attached at either end. So it functions kind of like a physical patch cable without you having to plug in the transceiver separate from the optic. We also have a number of cables that will operate as breakout cables so that you can split a 40 gig port into 4 10 gig ports, or 100 gig port into 4 25 gig ports, and so on. So when we're dealing with the cables, you're typically going to have the most common set of cables out there is going to be the duplex cable, which is literally just 2 strands of fiber, each one being wrapped up in a separate sleeve. And the most common connectors that you're going to see are going to be the LC connectors, or what's referred to as LC. It's the lucent connector. I'm sure you've seen these all over the place in the data center. It is the most common connector these days. There was an earlier connector called SC, or standard connector. And this has supplanted it because it is smaller, narrower. It's a little bit easier to work with. One of the nice things about this connector is you can always swap the polarity of the cables. So you can see one of these cables on the top here has a little white sleeve around it, and the other one has a yellow sleeve. You can actually swap the position of those 2 fibers on that connector if you need to change the polarity of the connection. One of the things that you're going to see in some of the more recent with some of the more recent transceivers that we have coming out is something called the Corning Sync-Out connector, or CS. And it's also a duplex connector, but it is designed with a much smaller physical footprint. So it's about 40% smaller than the LC connector. And so the practical upshot of that is I can actually take what in the space that I would have been able to fit a duplex LC connector, I can now fit two duplex CS connectors. So this diagram here on the left shows a QSFP shaped hole basically. And it shows that you can actually fit two CS connectors, whereas you'd be a little bit further harder pressed in order to fit if you wanted to try to fit two LC connectors. But one of the things that you should be getting used to if you have not been working with them in your data center yet is the multi-fiber push-on connector. And the reason for this is that most of the signaling standards out there today that have gone from the 100 gig speed range up into the 400 gig and then on into the 800 gigs, those standards are going to be using more than two pairs of fiber. So in order to support those, we have what's called a multi-fiber push-on or MPO. This is going to have multiple fiber strands in the cable, and there can be multiple. So you can have 8 strands, you might have 12 strands, you might have 16 strands, you might have 24. And depending on the number of strands in the cable, that connector is going to have a different number. So an MPO 12 uses 12 strands. If you use an MPO 24, it has 24 fibers. So if you are using a signaling standard that uses 8 strands of fiber, as typical for things like SR4 or LR4, what you'll have is typically you're going to have an MPO 12 connector, which is technically something that can support 12 strands of fiber, but you're only going to use the outer 8 strands of it. Sometimes some vendors will actually make a cable like shown in the middle of the screen here, where it's the same physical size as a MPO 12, except they didn't put the 4 strands in the middle, knowing that they wouldn't actually be used. That's fairly rare. Typically, you're just going to have a standard 12 fiber cable, and you're just going to ignore the 4 fibers in the middle. The gender for the MPO connector is determined based on these pins. So if you have a pinned connection, the pins go into these matching holes on the other side of the connector. So typically with an MPO connector, you're going to have the pins are located on the equipment side, whereas connectors for other types of media are typically going to be the pinned side is actually going to be the cable. In the case of MPO, it's on the other side, so that the gear that you're plugging into will have the guide pins on it. There's no official standard on that, so basically when you buy these cables, in many cases there are ways of removing the pins or adding pins if needed. So there's just like a little cage in the back that kind of has a spring-loaded mechanism that locks down those pins, and there's little tools that you can use to pull the pins out. It's also worth mentioning that the MPO standard is the standard, but then there's a trademarked version from US Connect called Multi-Fiber Termination Push-On, or MTP. MTP is completely interoperable with the MPO spec. So you can take an MTP cable and plug it into an MPO connector on a device, and it's no problem. What it is just they made some mechanical improvements to the connection type. So you can see on the left-hand side on the bottom here, you can see that the MTP guide pin is a little more rounded as opposed to this kind of squared off guide pin for MPO. They made more room for the ribbon cable if you're using a flat ribbon. They improved some things on the spring clamps holding in those pins that I mentioned earlier. So Typically what you'll find for sale is usually going to be MTP rather than MPO, just because people like those improvements. So when we were working with the LC connector, when we had a duplex set of fibers, then all you had was two types of polarity. It was either flipped in one direction or another because you only had the two fibers. When you have 16 or 20 or 24 fibers, then, or however many fibers you have in your MPO connector, now you have to worry about polarity in a different way, right? So there is the way we align polarity. If you look on the top right here, you can see that these cables have a little white dot on one side of them. That little white dot is where the first of the fiber, it's canonically where the pin 1 or the first fiber is coming through that connector. So if you have a connector that is, the connector is keyed. So basically, if you have this little part that sticks up on the connector, that's called a key. And if you have it in the key up position, then the key is up with the white dot facing the left. So if you were looking straight into the fiber, which you shouldn't do because it's bad for your eyesight, if it happens to be lit from the other end. But if you were looking at the end of the cable, you would see that the first fiber is considered in position 1 because it's closest to the white dot. If you have like a cable that is a full straight through, then you might have a cable where one side of the connection is flipped so that it is in the key down position. And that way you basically have a completely reversed polarity where the first pin becomes the last pin and so on. The most common polarity that you're going to have is this type B, which is reversed. So that is basically just flip this end over end, and your pin 1 on one side becomes pin 12 on the other. Pin 2 becomes pin 11, and so on and so forth. But there are other types of polarity. So there's a type A, which is just straight through, where basically pin 1 is pin 1 on both ends. This is typically only going to be used between patch panels in a structured cabling environment. You're typically going to have just those connectors at one end. Reaching to either patch panel on either end, and then you would use your, you can use the patch cables, which have a type B reversal to patch in there. If you see a type C is actually a different type of polarity, so they flip the pairs. So basically pin 1 and 2 get flipped, pin 3 and 4 get flipped, so on and so forth. This is not used by any of the devices that I know in the data center, but just be aware that if you see an option for a type C polarity on an MPO or an MTP cable, that's not the one you want. Typically, you're going to do any kind of device-to-device connections are going to use those type B cables, and they're going to be the female or the unpinned connectors. So when you get down to the actual fiber, depending on what type of connection that you have, it doesn't really matter whether you have a Lucent connector, a CS connector, or an MPO connector or an MTP connector. The ends of the fiber are going to be handled with what's called a ferrule. And a ferrule is just there to protect the actual fiber optic cable itself. And the ferrules will basically physically meet and touch when you're actually making a optical connection. So the ends of them are polished, and that way we can keep a clean signal. But over time, things have evolved. We started out with this concept of a flat fiber where we basically just cut clean across the fiber. Unfortunately, that results in some of the signal basically being reflected off of the cut end of the cable, or the cut end of the fiber, I should say, and reflecting some of that light back in. So this basically became untenable. So as time went on, we basically started to experiment with curving the connections in the way we polish the ferrules. So when you see a PC or physical contact indicated on a cable, that means that the ferrule has this very slight curve to it that actually does help reduce the amount of light reflected from the end. In more recent years, it's gone to what we call ultraphysical contact, or UPC, where we actually increase the curve and got a massive decrease in the amount of light reflected from the end. But nowadays, for the highest speeds and for things like 400 gig, typically what you're going to find is something called an angled physical contact. And this is basically where we slice the cable at a 8-degree angle. It gives us even less light reflection than the ultra physical contact did. The downside to this is that it introduces an orientation to the cable, whereas if you plug it in the wrong way, then you have the potential to actually physically damage the ferrule when you connect it in. So PC and UPC ferrules are not interoperable with APC. So if you see a cable with an APC connector on it, don't try to plug it into any kind of like fiber patch cable port that has a different one. How you can tell what type it has is we actually do a color coding. So if you see an aqua or a blue connector with a ferrule sticking out of it, then typically that's going to be a PC or a UPC connector. Doesn't matter which one it is, it will actually interoperate. You can connect a UPC and a PC connector, it's no problem. But if you see a green connector, then that is an APC, so it's going to have that angled connection, and you have to be very careful about how things are plugged in. You can see on the bottom right there, there's a diagram showing a close-up of what happens when you have an APC to APC mated correctly in a patch panel. And then what happens if you took a UPC and mated that with a APC connection. And you can see the physical gap there, and the fact that the connector for the blue cable is kind of pressing in on the tip of the connector for the green cable and probably causing some physical damage. So it's very important to note the connector, the end of the cable. The housing is actually going to determine the color of that housing is going to tell you what type of ferrule this has. So speaking of colors, the cables in your data center are going to have a color coding as well. So we started out with single mode, and single mode has always had a yellow color cable jacket. And then depending on the connector, it's either going to be blue or green. And remember that green gives you that APC type of ferrule polish. Very common in the data center, at least for, several years ago, would have been the orange cables, and the ubiquitous orange cables are going to be multi-mode. They are either going to be 62.5 or 50 micron multi-mode. If you find an orange cable with some beige connectors, it's probably not going to work well for anything that you want to plug it into today. But we do have some of those cables laying around in our labs that I've seen. So just be careful. The orange and black cables are usually okay. Those are just going to be OM3 cable or OM2 cables, but you don't want to use those for any long distances. In fact, we kind of stopped certifying the OM2 cables. You really want to do OM3 or higher. So once you get into OM3 multimode cable, then you're looking at an aqua colored cable jacket. And then the connector on the end, it's before we started doing APC. So a gray connector is typically going to be the UPC connector. And then if you see a green housing on the connector, then that's going to be APC. We've gone to OM4, and the OM4 basically, it's going to be a higher quality cable. It's going to get your signal a little bit further, and the adopted color for that cable jacket is now violet. But when we first came out with it, then there wasn't really a standard for that. So a lot of times there are some OM4 cables that come with an aqua jacket. So just look at the writing on the side if you see an aqua cable to see if it's OM3 or OM4. There is also OM5, which I don't see very common in data centers just yet, but I do see more and more of it as time goes on. And the color for those cables are going to be lime green. Again, with each of these cables, if you see a green connector on it, that's going to be an ABC connector. So when you're working with optical cabling, we already talked about how you can have some light reflecting off the cut end of the fiber, and that is called back reflection. And the way we measure the signal in an optical cable is measured in decibel milliwatts or dBm. If you see any kind of loss ratings, you might not see a positive or a negative value on it, but just know that any measurement for loss is going to be a negative, where basically if it's 10 dB, you're going to lose about 1/10 of your signal, or it's technically minus 10 dB, so you're losing 1/10 of your signal. Depending on how long your cable is, you're going to have signal attenuation. And you might lose as much as like 3 decibels per kilometer. Do we have a question? No. Okay. You might lose as much as 3 decibels per kilometer on a long distance link just for the cable itself. And then when you plug in that cable into a patch panel or plug it into a device, you are going to have what's called insertion loss, and that's just from the mating of the two physical connections in the ferrule. So once you actually have those connections, you have to count the number of connections that you have, and that is going to determine how much insertion loss that you might have, and it could be up to 0.75 decibels per connection. And then if you're doing any kind of cable splicing, that's going to also introduce some insertion loss as well. And then you do have that return loss, like I mentioned, where you get some reflection off of the cut end of the fiber, but that is usually factored into the spec for the connector. So if you are looking at a cable and the spec of the cable says that it is, let's say the loss on the cable is for the distance of that cable is, let's say, minus 2 decibels, then you're going to know that the insertion or that the return loss is actually accounted for in the spec for that cable. So you don't need to count that, but you do need to count for insertion loss. If you want to know whether the signal coming to and from your devices is being lost at an untenable rate, then one of the things you can use is digital optical monitoring. So some of the more recent transceivers out there allow you to get specs out of the transceiver for its temperature, the voltage, the amount of current that it's drawing, and most helpfully, the optical transmit and receive power. So when you look at the spec sheet for a given transceiver, optical transceiver, it's going to give you what the full transmit power and the full receive power is. And then you can actually use a show interface command, at least in NXOS. I can't speak to the Catalyst or other devices out there, but for a Nexus device, if you do the show interface transceiver details, if it is a DOM capable transceiver, then you'll get these specs as well. And then you can compare the two ends and see, okay, how much transmission loss am I getting? If I look at the transmit power from one side and I look at the receive power on the other side, and then I do the math, I can determine exactly how much of a loss I am getting across that link. All right, let's talk a little bit about modular transceivers. So one thing to note with transceivers and pretty much everything that's going on these days in any kind of electronics is that most signals are now being used. We don't do parallel signaling anymore. Now it's all high-speed serial signaling, right? So when I'm making those connections, we are using what's called differential signaling. And that means that we're actually using 2 wires to send the signal, And we are using positive voltage and negative voltage on the two different wires in order to create a pulse that is different in each direction, on different directions for each wire, so that any kind of noise that might spike and add interference and add voltage to that line is not interpreted as a signal. It has to be a positive on one side and a negative on the other in order to count. So in order for us to send these signals, we have to use these pairs of wires. Whenever you have these pairs of wire traces, each pair is referred to as a lane. I'm sorry, two pairs are referred to as a lane because you have one transmit pair and one receive pair. So things like PCI Express and a lot of the Ethernet signaling I'll be talking about, these are all considered, a certain number of lanes for these transmissions. So the lanes that I'm talking about are referred to by the term SerDes, it stands for serialization, deserialization, kind of like the term modem stood for modulation and demodulation. And basically, when you have these SerDes lanes, there's groups of 4 wires. And some standards for signaling will actually only have to use one lane, and some standards may have to use multiple lanes. When I'm plugging in a transceiver, I am taking the electrical signals that are coming from the switching ASIC on the system board, going to the physical cage for that transceiver, and I am picking those signals up, and I am translating them, usually translating them to a different type of signal that is going to be sent over an optical connection, or potentially a copper connection as well. So if I have a switch with a given physical cage for transceivers, I might have a configuration where there's a single set of SerDes lanes going to a single physical cage, but I might need to break up that signal. So for example, in a model of switch that has 100 gig and 400 gig ports, maybe I have a 400 gig transceiver port and that's directly connected to the ASIC. But maybe I want to take the next 400 gig port on that ASIC and break it up into multiple 100 gig transceiver connections. In order to do that, we might put something called a gearbox on the system. So the gearbox is responsible for breaking up the lanes from the ASIC into additional connections for lower speeds. So basically, it's kind of like putting a breakout cable embedded on the system board. So the downside of the gearbox is that it will add a little bit of latency for your signal transmission, and it does increase the amount of power consumed and therefore the amount of cooling required. But it's better if you're trying to have a switch model that has different speeds of connections rather than having to build separate ASICs onto the system for handling the different speeds. Okay, the common transceiver formats that you're going to find in the data center today are going to be usually some form of SFP, which is called small format pluggable, or QSFP, which is quad SFP. And the SFPs are the ones that you're used to. We used to call them GBICs back in the day for gigabit interface connector. And basically, that started out life as the SFP supporting 1 gig. When we went to the 10 gig, it became known as SFP plus. Now you can actually take an SFP adapter or SFP transceiver and plug it into an SFP plus socket, and it will be backwards compatible for that speed usually. When we started going up in speed to 25 and 50 gig, then we stuck with the SFP form factor, but we changed the name a bit. So the SFP28 supports 25 gig, and the SFP56 supports 50 gig. So those are the connection speeds that you can get out of that format. Note that the 28, it doesn't say SFP25, it says SFP28, and the reason for that is you've got some signaling overhead that has to happen on the wire in order to get a 25 gigabit data rate. And similarly with the SFP56, it's accounting for that additional overhead as well. In the QSFP form factors, basically we started adopting QSFP when it was QSFP plus. So these were your 40 gig adapters, your 40 gig transceivers, I should say. And when we went up into 100 gig, we started using QSFP 28, which just basically took 4 SFP 28 signals and bound them together from 25 gig to 100 gig. And then the same thing when we go to QSFP 56, that's going to be 4 SFP 56s, which would give you up to 200 gig in speed. When we get into the 400 gig range and 400 and 800 gig, that's where things get a little interesting. You can see on the right-hand side on the bottom there is this new form factor called QSFP DD, or QSFP double density. And what happens is we took the QSFP slot and we basically extended it so it had a second set of connectors on the card. So the one on top being a QSFP DD, you can actually see where that the little dashed line kind of cuts that card in half. The farther back half is the second set of connectors for the double density connections. So that means I can take a standard QSFP transceiver and plug it into a QSFP DD port and be backwards compatible with being able to use that transceiver. But the QSFP DDs respectively run at, when you see a QSFP DD in Cisco speak, that is the 400 gig version. Technically, it's called a QSFP 56 DD. And then for the 800 gig connections, we call it QSFP DD 800. Technically, it's QSFP 112 DD, where each one of the signal pairs runs for 112 SerDes rate. If I wanted to run a single SFP connection out of a QSFP adapter, out of a QSFP port, I should say, we have an adapter for that. So there is a QSFP to SFP adapter that allows you to, you plug this into a QSFP port and allows you to plug in an SFP-based adapter and use one of the 4 lanes on that connection. So if you have a switch, let's say that's an all QSFP switch, and you want to be able to plug those in, this is the adapter that you would use for that. If you want to figure out exactly where this adapter is supported, what you want to do is go to the TMG compatibility matrix, and I'll show what that looks like in a little bit. But basically, we go up to this matrix tool, and we can plug in the model of device, and it will tell you exactly what transceivers are supported. And if it shows an SFP transceiver, you can actually look it up, and there'll be like a little tooltip you can hover over, and that will show you exactly which type of QSA adapter might be needed for that. We actually offer 2 different versions. One is meant for 40 gig to 10 gig, and then the other is 100 gig QSFP 28 to 25 gig SFP. If you go to tmgmatrix.cisco.com, if you guys have never used this tool, I highly recommend that you check it out. You can basically just punch in the version, device that you're using, and it will come back with all of the different transceiver product IDs that you can actually use with it that have been certified. It will tell you exactly what type of connector it is. It'll tell you how far the distance goes, the supported distance for the signaling. It'll tell you exactly what type of connector is used, and over here you can see, so for example, there's MPO12 with UPC with multi-mode fiber, and then down here you've got single mode fiber with an MPO12 connector, but it happens to be APC polished. So it's helpful to know. In addition, it will tell you whether it is DOM capable, and then which version of software was the minimum version required in order to support that on that platform, and then what the minimum version is, and it might be different in order to support DOM with that transceiver on that platform. And when you hover over something that is showing, let's say, I have a 100 gig port on a switch, and I hover over a 25 gig SFP, it's showing for QSFP ports, QSA 28 is required. So that is the SFP 28 or QSFP 28 to SFP SFP28 adapter. So I talked about QSFP-DD, right? The double density form factor. We have adopted that at Cisco. That is the spec that we're going with for our 400 gig adapters and on into 800 gig. There is another form factor out there called OSFP, or Octal Small Form Factor Pluggable. And you're going to find this in Arista and some other vendor switches. It is physically smaller than a QSFP or QSFP-DD. And there are some drawbacks to it, unfortunately. There is a higher maximum power consumption spec on it, but in order to do so, you need to actually put heat sinks on the actual transceiver. And then in practicality, when you try to run that at high speed all the time, then you start running into some thermal concerns with the design for the switches. So we stuck with the QSFP-DD. It is a wider form factor. It is going to be going to mean that we can fit slightly less ports on a switch, but at the same time, you wouldn't want to fit any more ports on the switch than we already have because of the thermal density requirements. And OSFP can kind of drive that over the limit. So it's very unlikely that you're going to see any kind of switches from Cisco that have OSFP. It is typically going to be QSFP-DD. So what happens if I want to communicate between two devices and one is an OSFP device and one is using QSFP-DD? The answer is use the correct transceivers from each vendor and just make sure that they are using the same signaling standard. So in this example here, I'm using 400 gig SR4. And so I have a QSFP-DD transceiver on the left side, an OSFP transceiver on the right side. They are both speaking 400 gig SR4. They are both using a 8 strands out of a 12-strand fiber optic cable, both using an MPO12 connector on either side, and they're perfectly able to communicate at 400 gig. So it really doesn't matter whether or not we have a switch that has OSFP in it. Your OSFP devices can be connected into a QSFP-DD based switch. You may see something called S-class transceivers. So in recent years, we started phasing out the testing for different adapters for different environments. We realized that the vast majority of customers don't have specialized requirements for, the Trade Agreements Act or specific temperature ranges or being able to use OTN, optical transport networks, or WAN-Fi. So we basically have released a class of transceivers that we end with a -S, and those are S-class transceivers, and those are going to fit the most common use cases for most enterprise customers. So there are some limitations to them, but they are definitely going to be cheaper than the non-S-class optics for the same type of signal. Another thing to consider is that when you get into, especially when you get into the 400 gig switches, even with the QSFP-DD ports, even if we're not putting so many ports on there that we can't cool it, it is still a harder task to cool these 400 gig switch models. So because of that, you might be limited in your airflow direction to port side intake only. So in that case, you would have to face your ports towards the cold aisle, and then have your fans and your power supplies at the other end facing the hot aisle, and that's the only airflow direction you can get. This usually isn't a problem because the 400 gig switch models are typically going to be, they're either going to be a core switch or they're going to be a spine switch, and those are typically going to be in a network rack where that tends to be the orientation for the gear anyway. Instead of being at the top of a server rack where all the cables are in the back. So just as food for thought, just make sure that you are remembering that when you're looking at adopting a 400 gig switch model. All right, can we go ahead and pause the recording. We'll take a quick bio break.
Percent.
All right. So let's talk about the actual the methods for transmitting data that the transceivers are actually using to send these signals, so that we can understand more about why the transceivers are named the way they're named, the part IDs are the way they are. They all kind of correspond to these various standards. So to begin with, when we want to put any kind of signaling on the wire, we have to figure out how to encode it, and translating the actual bits of data into the signals being sent on the wire. We actually use, typically in the past, have used all the way up through 25 gig Ethernet, uses what's called 64-bit, 66-bit encoding. And what happens is we would actually take 8-bit data blocks or control blocks. Those could be instructions for the communication stream. And we would take those 64 bits and we would add a 2-bit sync header, and that becomes a 64-bit block. And that's typically what will be put directly onto the wire. Now, we are having to make things a little bit more efficient in order to pass more data on the wire. So when we get into the 40 gig, 100 gig, and later into 400 and 800 gig, excuse me, we are using what's called 256, 257-bit encoding. And that is where we basically take those same 64 bits, we'll take another 3 blocks of 64 bits, we will combine those together into a 256-bit block, and then we will add a 1-bit header on the front. And so that's how we can actually put markers in the data stream and be able to send basically 4 times the amount of data before having to get to another sync bit, for example. In addition, you've probably heard the term forward error correction, FEC. This is sort of getting a bad rap when you're dealing with things like 25 gig, because 25 gig started requiring forward error correction, and because we are using these higher data blocks, and it really wasn't super standardized across the industry. So basically, there were different types of FEC, and there were different devices that supported the different types, and then there were different types of FEC that you had to turn on for different types of transceivers or cables. So it is a little bit of a mess, but with the 100 gig and 400 gig, things have been a lot more standardized. The current standard that everyone has settled on is called Reed-Solomon forward error correction, or RS-FEC. And here's basically the way it works. So the sending device is going to take about 40 of these 257-bit blocks, and it's going to string them together, and it's going to start processing them. What it's going to do is it's going to pass it through a scrambler, which is going to run some math on it and basically try to increase the signal entropy so that you don't have long strings of zeros or long strings of ones. We want to actually make sure that the link is being well utilized, and we're flipping the bits as often as possible. So the scrambler only exists to increase that signal entropy. Once I have my scrambled blocks, I start actually feeding them into not one, but 2 different FEC engines. So those different engines, basically every 10 bits that I get out of the scrambler, I'm going to send to one engine or the other, and then I'm going to alternate back and forth between the 2. Each one of these engines is responsible for taking those 10 bits that I just fed it and assembling them into what we call code words. And the code words consist of 514 of those 10-bit data symbols. And then we calculate parity on that. And the parity, depending on the speed that you're running and the standard that you're using for your signaling, it's either going to be 14 or 30 symbols worth of parity. So at the end of the day, you're going to wind up having a 528 or a 544 symbol code word, and that includes your data and your parity for calculating any kind of lost data from it. And that is basically how we're doing the error correction on the signal. So once we have those code words, then what we do is we then round robin distribute those symbols on 16 channels to what's called the physical medium attachment layer. And basically we alternate those bits across those 16 channels. And the physical medium attachment layer is responsible for translating that into the number of lanes for that signaling type of media. So basically within your transceiver, if I'm, let's say, for example, running a 100 gig SR4 connection, then that uses 4 lanes. And that means that I'm going to take each of these bits that got spread out by the PMA or to the PMA, and it's going to basically order those across those 4 lanes and send the signal down the 4 lanes. Once the signal gets to the other side, we basically reverse this entire process. We collect the bits, we send them back up through the FEC engine to calculate and see if the parity matches, and if there's a mismatch, to use the parity to reconstruct some of the bits, and then descramble the code stream, and then I have my data block again. So there's a difference in terminology. We are very used to thinking in terms of gigabits per second, megabits per second, etc. And that's typically been the most common way of thinking about it. And the reason why is our line rate has always tended to match our data rate, at least in the data center. So line rate is basically how many signals I can send on a wire or down a fiber optic cable, right? So it's basically how often can I flip those bits? How often can I change the voltage on a wire? How often can I send a pulse of light, right? And that is measured in what's called baud, named after the person that developed the concept. And then data rate is a measurement of how much actual information can be sent per second, and that is then generally going to be measured in bits. If I can only encode 1 bit in a given signal, so let's say my voltage goes high, it's a 0, my voltage goes low, it's a 1, my voltage is nothing, then I have no link. Then that means that for each signal that I send on the wire, I can get 1 bit of information out of that. If, however, I can encode that signal differently, so let's say I use something called pulse amplitude modulation, 4-way pulse amplitude modulation, or PAM4, then what I can do is I can actually encode 2 different bits in every signal. So I have, let's say, 4 different levels of voltages. Each one of those 4 different levels can be encoded for a 00, a 01, a 10, or a 11. Now all of a sudden I can actually get 2 bits of data for each one of those voltages, or for each one of the signals that I send down the wire. So now all of a sudden I've doubled my bit rate in comparison to my baud rate. So the mechanism by which we map 1 bit to each signal is what we call non-return to 0. So non-return to 0 is basically either I have a positive voltage or a negative voltage, and if there's 0 voltage, then the link is considered down. So typically throughout history, this is the way Ethernet has worked. With the 4-level pulse amplitude modulation, or PAM4, now I get to use 4 different levels of voltage, or 4 different intensities of light, and that is going to allow me to send 2 bits per signal. So the problem with using a signaling method like PAM4 is, okay, I've got these 4 different levels of voltages or 4 different intensities of light, and the challenge with that is that because they're so much more close together, it's a lot more susceptible to noise. So in order to do that, that's why we have those additional parity symbols in the FEC code word. So whenever I'm going to be working with a signaling standard that uses PAM4, then that means my FEC code word is going to have a 30 parity bit or 30 parity symbol. It's not bits, it's actually 10 bits each. So it's actually going to be about 300 bits worth of parity instead of 140 bits worth of parity. So no, this is an eye chart, but this is basically some of the most common specifications out there. So the IEEE working groups develop a standard. That standard is referred to as, contains a physical layer specification for how you're going to send a signal. So the naming of this is basically, it's usually referred to by the speed first. So 10G is 10 gigabit. The base is referring to the fact that this is a baseband signal instead of a broadband signal like you get from your cable provider. And then the letter that is used used to designate a particular type of medium and distance. So each one of those is given an effective throughput in or data rate in gigabits per second. And then the actual line rate that is being used to transmit all the symbols is going to be slightly higher than the bit rate, because remember we have those additional extra bit for every 256 bits. If I want to get 10 gigabits per second, I have to account for all those additional bits that are not the data that I'm trying to transmit. So there is always an additional overhead, right? So with a 64, 66 bit, then I get about a 3% overhead. So that's why it's 10.3125, because I have a 3.125% overhead on how much signaling I have to do on the wire to pass the amount of data that I intend to. So it goes throughout all of these different means. So these are the different ways that we're doing the signaling. And you'll notice when we get down to the ones that use PAM4, now all of a sudden I'm using this 256, 257 bit encoding, and I'm basically suddenly dropped that to about 10% of what the overhead was on an NRZ signal. So that basically means that I've got I have less overhead for the control bits that are going through the signals, but however, I'm actually having to pass more data that is parity. So it actually winds up evening out. So really, if I want to pass 100 gig, I can send. It's a double data rate with 2 lanes, and those 2 lanes can operate at 26.56. If you do the math, that actually winds up being about a 3% overhead on, the 3.125% overhead instead of 0.39. And that's because we had to increase the amount of parity bits in the stream. So regarding those letters at the end of the name of the standard, if you see a given suffix, it is based on usually when you come down to the optical standards, then it's usually changed based on the reach of the fiber and the signal within the fiber. So you start out with what's called very short reach, which is a relatively new standard for the IEEE. Cisco is selling transceivers that are meant for short link connections to servers, for example, from the switches at the top of the rack, and we indicate those with an SL or short link. The official standard for this is going to be called VR when you're looking at the signaling standard. So I would imagine that name might change at some point in the future, so that you'll start seeing optics with a dash VR on the end of it for the Cisco Part ID. Other than that, we have more typical ones. So SR is short reach. It goes up to 150 meters. And then once you start getting beyond 150 meters, we can no longer use multimode fiber. So we are actually going to go for DR, which is considered data center reach, which goes 500 meters, FR, fiber reach, goes 2 kilometers. LR, which is more traditional, that is long reach, and that can go up to 10 kilometers. All of these are using single mode fiber. And now there are things such as extended reach, or ER, which can go up to 40 kilometers, and ZR for zero dispersion shifted reach, and that is will take you all the way up to 80 kilometers. That is actually not a IEEE standard nomenclature. The ZR is part of what we call a multi-source agreement. So it's not an IEEE standard, but enough vendors have agreed on it outside of the IEEE that it is a accepted standard. In addition, you have CWDM and DWDM. This refers to coarse or dense wavelength division multiplexing using multiple frequencies of light on the same wire. And these are supported. CWDM gets you 2 kilometers and DWDM can get you all the way up to 80 kilometers. If you see BiDi in the name of a transceiver or as part of the part number or part ID, then we are actually using bidirectional wavelengths. So basically it uses the same pair of fiber optics. And for each one of those fibers, we're actually passing 2 different wavelengths of light, one in each direction. So it gets us the ability to do some bidirectional capability. And that allows us to pass more data over less fibers. So we can actually go back to using multimode fiber. Oops, excuse me. We can go back to using multimode fiber. And it's still limited to 150 meters, but we can usually pass faster signals over that same distance. Now, we actually had a BiDi transceiver, or a set of transceivers that were developed at Cisco, actually. So BiDi was basically a low-cost way of using wavelength division multiplexing on a single set of optical fibers. So when I'm using the transmit direction and the receive direction, they're using 2 different wavelengths of light on the same fiber. And so that's nice because now I can get 2 lanes instead of 1 for each fiber. For the 40 gig BiDi, we were able to do basically 40 gig over a single pair. And then the 40/100 gig BiDi was able to do the same thing using 25 gig signaling. And that was backwards compatible with the 40 gig BiDi. However, BiDi has now been adopted by the IEEE. So the IEEE standard for BiDi is 100G base SR 1.2. And note that that starts at 100G, which means that it's 100 gig and not less. So there is no interoperability with the Cisco 40/100 gig BiDi and the new IEEE 100 gig SR 1.2 BiDi transceivers. Cisco offers both. We are actually deprecating our older 40 and 40/100 gig BiDi in favor of going with the IEEE 100 gig one. So when you're looking at 100 gig connectivity, unless you have a whole bunch of devices that are still using the older transceivers, please consider using the IEEE based ones, the SR 1.2 transceivers. Now, that can also interoperate with 400G base SR 4.2 because it's basically just 4 lanes of SR 1.2. And so I'll talk a little bit more about that regarding our breakouts. The other thing is, being 100 gig, it's not going to go back to, you can't use this for a 40 gig speed connection. It has to be 100 gig. All right, so as mentioned, you guys will be getting a copy of this deck. If you go into Appendix 1, you will see a list of Cisco Ethernet transceiver PIDs and a whole lot of details about what standards they support. Let's talk about breakout. So your breakout connections, in some cases, especially if you're doing QSFP-based switches, some transceivers that have multiple transmit and receive pairs can be split off into 4, usually because it's typically going to be something using 4 lanes. Anything using 4 lanes can usually be split. So basically, if I have like 40G base SR4, I can split those into 4 10G base SR. The 4 on the end of that SR4 indicates that it's using 4 separate lanes, and the SR without the number on it just means that it's using 1 lane. So we can actually combine those and split those out. 400G base DR4 can be split into 100G base DR. 400G base SR4.2 can be split into 4 SR1.2 fiber pairs. So when you're going to do any kind of breakout for a 400 gig switch to 100 gig switches, then that would probably be one of those last two is probably what you're going to use. Here's the thing, you can only break out connections if you are in a port that supports being able to use that connection as a breakout. So not every switch and not every port on every switch can actually use the breakout capability. Remember I mentioned that gearbox on the system board? That gearbox can actually because it already is basically doing the breakout, if you typically if you have a gearbox on the system board and that's driving your ports, then the ports driven by that gearbox are not going to be able to do any kind of further breakout from that point forward, right? But if you have a QSFP-based switch port or a model that just doesn't use a gearbox at all, then that means that most of those ports would be able to support breakout. And it's limited based on the switch model as well as the version of OS that you're going to be running on it. So make sure that you check your configuration guides, and those will give you the notes as to what model of switch and which one of the which model of switch and which version of software that you're running on it that will support the breakout capability. So not every transceiver that we offer that uses a breakout capable standard. So the example here I've used is the QSFP 40 gig SR4-S. That is not a breakout capable transceiver. So the 40 gig SR4 is, the -S is not. So always make sure that you're checking that TMG matrix tool in order to see exactly which version will support the breakout. Another thing is something that we call auto breakout. We have this auto breakout feature on NXOS. So basically, if you are plugging in the lower speed devices first on the 4 ends of that cable, and then you plug in the higher speed device at the other end, the higher speed device should notice that it's connected to 4 separate devices and then automatically set that port into breakout mode. Also, if you're using ACI in the data center, be aware that you can't use you can't use the last 2 ports that are used for fabric uplinks to support breakout. And because the switches are normally designed to operate with multiple fabric uplinks, so let's say, for example, I have the 93180. I've got my downstream ports on my SFP ports, and then I have my QSFP ports. My QSFP ports by default are going to be configured as fabric ports or uplinks to a spine. So I actually need to apply a port profile in ACI in order to get some of the lower QSFP ports to operate as downstream ports or access ports and therefore support the breakout feature. If you do actually do that, you cannot use those ports to connect to the APICs. The APICs have to be plugged directly into a standard port, so a standard SFP port, for example. Another thing is, if you're going to use splitter cables, then as you typically do for breakout, where the cable splits is actually a known quantity. So for the shorter cables, typically we will split 1/3 of the way along the cable from the higher speed end. So from the QSFP side, about 1/3 of the way it breaks out, and then each individual cable from that point going to each SFP is going to be split from that point forward. If you're using the longer cables, that are higher than 3 meters, then typically the split will happen 3 meters from the lower speed end. So basically, if you're using a longer cable, that means that we have 3 meters of cabling distance from the split to the actual SFPs, which is usually enough to get you basically all the way up and down a given rack. So the split would basically happen once you actually reach the rack for the target devices. If I'm doing any kind of fiber cabling, how does that actually, how does that work, right? So how do we do the pinouts for the splits for the breakout cables? And here's how it works. Pins 1 and 12 are going to go to the first split, pins 2 and 11 to the second split, and so on and so forth. And we work our way in from the MPO connector, and those map out to the specific SFP connectors. And if you guys have the copy of this deck, I made that a clickable image. So if you click it, it takes you to a white paper that explains all about breakout and exactly how everything gets split up. Now I mentioned that there's a standard for very short distances that's or what's called VR, 10G base VR or 100G base VR. Cisco offers these short link transceivers that are basically meant to do the same thing, where basically we start with an SR transceiver and then we just dial down the power on it essentially. So basically it allows us to consume less power and it's because the signal doesn't have to go that far. So starting with any kind of split out from 100 gig to 4 by 25 gig, we are not actually going to do any more active optical cables. So we are actually going to use a optical splitter cable, and we offer these bundles now that actually have one of the high-speed transceivers and then 4 of the lower-speed transceivers all bundled together with a discount. So if you guys are looking to do breakout and you want to do optical connections, this would actually be a good thing to look into. In addition, if you're going to do breakout, something to look into is our breakout patch panels now. So we actually have these devices now where we can split out, we can take the breakout connections and put it into a structured format for data cabling. So each one of these devices takes up to 6 cartridges, and each one of those cartridges takes up to 3 breakout cables. And so you can actually support in 1 RU, you can support up to 72 breakout ports. And if you go up to 3 RU, then you can get up to like 216 of them. So, you know, this is definitely something to look into if you want to avoid the cable mess that you can get by having a large number of breakout cables. In addition to that patch panel, now we also sell cabling. So I was surprised when I first joined Cisco that Cisco didn't actually sell any of the fiber optic cables. We actually always partnered. But now that we sell that, now we actually have the ability to sell the fiber optic cables that we can put in the data center. We can sell them. We offer lengths up to 30 meters. And we have different types. So we have single mode fiber, multi-mode fiber, LC connectors, MPO12 connectors. So there are some transceivers that take connectors that we don't support with these cables, but the vast majority are covered by this. And that also includes the breakout cables down at the bottom there. I'm sorry, breakout cables for both single mode and multi-mode fiber. And then in the deck, Appendix 2 covers the various breakout parts that I was just talking about. All right, let's shift gears now. So let's talk about the Ethernet twisted pair, 10 gig Ethernet twisted pair. So if I have 10G base T in my data center, which I feel bad if you do because it is very wasteful for power. But if you have devices that you need to support that have 10G base T, then there's a couple different ways of going about it. So the preferred and recommended method would be to just get a switch that actually has the 10G base T built into it. So we actually have, we've got two different models that support 10G base T, and then of course, if you're using 1G base T, then we also have another model that does that, the 9348GC. Actually, we have FX3 models now. They're a new generation of that. But let's say, for example, I have only a handful of devices there, and it's not worth buying a separate switch just to handle those connections. Well, we do actually offer a transceiver that can be used for 10G base T. And customers have been asking for this for a while. But the downside to this is that they take a lot of heat and a lot of power. So unfortunately, because each one uses about 2.5 watts each, you actually have some placement restrictions. So the surrounding ports that you have when you plug one of these in, the port to the left or right of it and the port below or above it actually needs to either be empty or running direct attached copper cables. So those would be those passive copper twin X cables I was talking about in the first slide. So if you're gonna run optics, you're gonna have to vacate those ports around any of these transceivers. So again, this is more for a reference, but this is basically the eye chart for the models that support it and exactly what ports you can plug them into. And to give you an idea, here's how the layout looks. So if you look at the yellow ports are where we can plug in the SFP plus the 10G base T transceiver, and the blue ports would have to be either turned off or only running copper DAC cables. Okay, so let's touch a little bit on fiber channel, and then we'll wrap up. So just as we have the Ethernet signaling specifications I talked about earlier, fiber channel has its own specifications. And something that it confused me initially, and I get some customers that get confused by this a lot as well. Fiber channel, let's say they take the salesy approach. They measure their speed not by gigabits per second, but by a measure of the number of megabytes per second effective throughput. So when you actually are working with fiber channel, 8 gig fiber channel is not actually operating at, well, actually 8 gig fiber channel is operating at 8 gigabits per second. But then when you start getting up into things like 16 gig fiber channel, now all of a sudden you start seeing that the actual line rate doesn't seem to match up with the number, right? So we're actually transmitting at 14 gigabits per second, but they're saying 16 gig fiber channel. So the math does work out. It does get you about 1600 megabytes per second throughput. But because it's not being measured in gigabits, it kind of throws people off when they do the math. But in any case, we have speeds that are up to 64 gigabits, 64 gig fiber channel, which is 6,400 megabytes per second of throughput, and that's currently the state of the technology today. They're working on the 128 gig fiber channel standard, so that should be ratified sometime this year, and then we should start seeing equipment come out from the vendors over the next several years. And if you want to run fiber channel, like native fiber channel on Nexus switches, there are a few models that can support it. So the first would be the 93180YC FX. Notice that that is not the FX3. That is not the model that is currently for sale. It actually went end of sale in July of this year. But if you have those in your environment, those can do native fiber channel. They have to operate in groups of 4. So if you change the ports to fiber channel, supporting fiber channel transceivers, you have to do so for all 4 ports. of each set of 4. We have the 93360Y CFX2 that is currently sold still. It's probably going to have a pretty long lifespan. We have nothing else that really matches that density for SFP. So the 93360YC, you can do it. Same thing applies where basically a set of 4 ports have to be converted over to fiber channel at once. So you can't actually just mix fiber channel and Ethernet in, that set of 4 ports. And then we also have the 9336C FX2E. The -E version of this added fiber channel support. And this is a bit of an odd beast because this is, as you know, a QSFP-based switch. And most of the fiber channel connections out there are going to be SFP. So in order to do this, we actually support a 4x 32 gig fiber channel breakout transceiver. And I'm a little bit hesitant on that only because there's not a whole lot of documentation surrounding that. And not a lot of vendors use breakout for fiber channel. So it is a possibility, but I think I'd probably opt for the 93360YC instead and just stick with traditional 32 gig fiber channel SFPs. Now, here's a question. I don't know if any of you guys know this, but why might there only be 3 models of Nexus 9K that can support fiber channel? Anybody care to give it a guess?
I'm not certain, but I love the "Here Be Dragons" comment.
Yeah, it's kind of off the map, so that's why I put that on there. Well, the reason for this is basically the Nexus 9K. When we first started out with the Unified Computing System (UCS), when we did the fabric interconnects for those, they were based on the Nexus 5K. And then over time, as we introduced the Nexus 9000, we had to come out with newer versions of the fabric interconnects based on the Nexus 9000. And part of UCS is that fiber channel is kind of mixed in with everything. So it is it's a combined device, the fabric interconnect, that does both Ethernet and fiber channel. So typically, if we didn't have UCS, we probably wouldn't have any Nexus switches that support fiber channel at all. It would just be the MDS switch line. But because of the need for having a UCS fabric interconnect, we had to have certain models of Nexus switches that those fabric interconnects were based on that supported fiber channel. So that is why we only have 3 models, because those became the UCS 6400 and 6500 fabric interconnects respectively.
Makes sense. Got it.
And if you want a list of fiber channel PIDs for the transceivers, then go ahead and take a look at Appendix 3 in the document. And that's all I have for you guys. So are there any questions that have come up that we weren't able to answer with chat?
I think everything got taken care of in chat. And I want to thank you again, Brian. It's pretty inspiring to see someone who knows that technology this kind of deeply and is this passionate about it. You don't always get that anymore these days, and maybe it's just my age talking, but I sure appreciate it, and I appreciate you taking the time to come share with the group.
All right. Well, thank you very much.
Need help? Call our cybersecurity team and book a consultation with us today.